Okay, I hear the recording in progress. So we'll share the screen and get started. Okay, welcome to November, which means we're ending very soon. I believe we only have 6 weeks left. 1, 2, 3, 4, 5, 6. And those 6 weeks have lots of holidays also. We have a Veterans Day next week. We have a Thanksgiving a couple weeks after that. Okay. All right, so first, you should have gotten an email back from me about exam 4. If you did not, let me know right away. But I've graded your exams, sent you an email back, and I sent a video. Okay, so if you're missing anything, let me know. There's only one more major exam. Remember, you get to drop one exam, which it does not include the final exam. You cannot drop the final. Well, technically, that's not true. You can drop part of the final, but not all of the final. Okay. Schedule-wise, we're down to our last chapter, but it is a long chapter, as you can see. However, I think if we go at the pace of 2 days per section, so if you notice my calendar, 2 days for 11-1, 2 days, 2 days, 2 days, okay, we should be fine all the way through. Not sure now whether we're going to have the last exam on Thursday, the 9th of December or Friday the 10th. When I made the schedule out, it was assuming we were face-to-face, in which case I would hurry up and try to finish the exam and give it back to you Friday for grading purposes, but that's no longer necessary since we're remote. And even if I don't get you your exam back, in fact, if I give you the test on Thursday the 9th, I'm pretty sure I'm not going to be able to get it back to you Friday, but it shouldn't matter. You'll get the solutions video, and sometime the following week, you'll get your exam, but you can still study for the final exam, which for us is Friday the 17th. And please notice you get 2.5 hours for the final from 8:10 to 10:40, okay? So that's where we're at. And we will begin our last chapter, chapter 11, which is on sequences and series now. Okay, here's the homework. And presently get started with that. Okay, chapter 11, our last chapter, but it's a long chapter. So on infinite sequences and series, bottom of 693, that picture. 11.1 is on sequences. This is the only section that's on sequences. The rest of the chapter is on series. Okay, so we're doing sequences now. Okay, so a sequence can be thought of just as a list of numbers in a definite order. Okay, here's a notation. Page 694. A1, A2, A3, A4, dot, 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 AN, meaning the first term, second term, third term, nth term. Okay, that's all there is for a sequence. Just give a list of numbers. Okay. Quite often there's a rule associated with the sequence. You could also write it as braces A sub n, or braces A sub n, n equals 1 to infinity. Most of the sequences we're dealing with, we're going to infinity, and once in a while we won't. We'll stop after a certain amount, but we're interested in what happens as n approaches infinity. Okay, so in these examples, some sequences can be defined by giving a formula for the nth term. Okay, so there's a bunch of sequences. How do I get the terms? You can just plug in. Okay, you can write it either this way or this way. I like this way better, it's more compact, but they mean the same thing. This A sub n, n equals 1 to infinity. You can even leave off the n equals 1 to infinity like this does. Okay, but you just plug in. So for instance, if I plug in 1, you get 1 over 2. Plug in 2, 2 over 3. Plug in 3, 3 over 4, and so on. In general, n over n plus 1, right? Here's B. They can write it like this with the braces, or like this. Let's take a look at that -1 bit. What's a -1 do? Well, -1 to the first power is -1. -1 squared is 1. -1 cubed is -1. -1 to the fourth power is 1. So it makes the sequence alternating, alternates plus, minus, or so on, right? So notice it goes negative, positive, and so on. Okay. And you might say, oh, I don't want the first one to be negative, I want it to be positive. Well, a trick around that is to make this exponent, instead of n, you can make it n plus 1, or sometimes n minus 1. Okay, so if I put n plus 1, if you plug in 1, you'd have negative 1 squared, which is 1. Okay, so negative 1 to the n, or n plus 1, or n minus 1, makes a sequence alternating, bounce back and forth between positive and negative. And then here's all the terms of the sequence. Okay, square root of n minus 3. Here they're starting with n greater than or equal to 3 because you're not allowed to plug in 2 or 1 or 0 and so on. Okay, so these are just some sequences. You just basically plug in. Now later on, shortly, we might want to be interested in what happens when n gets big. So if you look at this sequence, it's clear when n gets big, the terms approach 1, right? 3/4, 4/5, 5/6, 100 and 100 over 101, a million over 1,000,001. That fraction is very close to 1, right? So we would say that the sequence converges to 1. Okay, most of the time we might start at 1. I mean, it's natural. We say first term, second term, but you don't have to. Here we're starting at 3. Okay, and later on, way down the line, toward the end of this chapter, we're going to be starting indexing at 0 most of the time, actually. And you computer science people know quite often you start at 0 rather than 1. Okay, so if we don't say otherwise, normally we will assume for now that we start a sequence at 1. Maybe 1 is not allowed because something like this, you're doing a square root of a negative. Okay. Or we like to start at 0. So later down the line, we will be starting at 0 quite a bit. Okay, so let's take a look at some of the first problems. Then we had to go up to 78. So page 704. Let me show you the homework for those of you who don't have the book and are planning to get it. That. And somewhere there. Whoops. This up here. Okay, 19 to 21. Sorry, I'm practically holding the book vertical in order to see it. I think you can still see that. Yeah, starting with 23, it says find the limit. So you're taking the limit as n approaches infinity. Okay, we'll use that term converge or diverge quite a bit. Converge means we get a real number. Diverge, we don't get a real number for the limit. Some more. More. And some more here. Okay, we'll see this word again. Convergent, divergent, converges, diverges, converge, diverge. They converge, we get a real number. Diverge, we don't get a real number. Okay, we'll use that word over and over and over again in this chapter. Okay, and how far do we have to go? 78, I think it was. Okay, now the first few problems should be fairly straightforward. List the first 5 terms of the sequence. Just plug in 1, 2, 3, 4, and 5. And then whatever it is whatever it is, right? What could be easier, right? All right, so sequence and series. There's 3 star. I put a star meaning probably not exactly the same. And it isn't. But you kind of get the gist of it. So the directions say give the first 5 terms of the sequence. Plug in 1, 2, 3, 4, and 5. Okay, so plug in 1, you get 2 over 2, which is 1. Plug in 2, you have 4 over 5. Plug in 3, you have 6 over 10, which reduces to 3/5. Plug in 4, 2 times 4 is 8. 4 squared plus 1 is 17. Plug in 5, you have 10 over 26, which reduces to 5/13, and etc. Okay, so here's the first 5 terms of the sequence defined by this rule. So of course you can find any term of the sequence that you want. Say, what's the 1,000,000th term? Just plug in 1,000,000. Right? And yes, the implication is that you're plugging in only positive integers, so you don't plug in a half or pi, right? These are terms, so terms have to be stuff like 1, 2, 3, 4, natural numbers, right? Or sometimes whole numbers, including 0, as the case may be. Here's number 5. A sub n is -1 to the n minus 1 over 5 to the n. let's just think about the -1 stuff. Okay, so if I plug in 1, I'm taking -1 to the 0. Anything to the 0 is 1. If I plug in 2, I'm taking -1 to the first power, which is -1. If I plug in 3, I have -1 squared, which is +1. So again, this is a trick to make the sequence alternating, but beginning with a positive. So it's positive, negative, positive, negative, positive. Okay, for the numerator, it's either 1 or -1, right? And then the bottom is easy: 5 to the 1, 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th, and so on. All right, I have to take a little diversion and talk about the factorial function, n factorial. We'll see that quite a bit in this chapter. So number 7 there, a sub n is 1 over n plus 1 factorial. The exclamation point means factorial. Okay, so let's review what is factorial. It's defined for whole numbers. What are whole numbers? 0, 1, 2, 3, and so on. Okay, those are the whole numbers. Okay, so there's no such thing as -1 factorial. There's no such thing as pi factorial, a half factorial. They don't exist. Excuse me. Okay. So what is this? By definition, 0 factorial is 1. Okay. Why? Because we said so. Right? But it actually is a good definition, as we shall see later. Okay. 1 factorial is also 1. How come? We said so. So right now it's not very interesting, it's just 1. But now for n greater than or equal to 2, the factorial function becomes interesting. Okay, so n factorial for n greater than or equal to 2 is 1 times 2 times 3, ... all the way up to n. You just multiply them all up to n. Or you could start at the top, n, and then go n minus 1, n minus 2, until you reach down to 1. Okay. And I have some examples here. Okay, so 2 factorial is 1 times 2, which is 2. 3 factorial, 1 times 2 times 3, 6. 4 factorial, 1 times 2 times 3 times 4, 24. I would probably say you should get very comfortable with these numbers. It's going to show up over and over and over. Okay, this last chapter that we have. These, not so much, you don't have to worry about them too much, but you know, if you want to, you may. 5 factorial, 1 times 2 times 3 times 4 times 5, 120. 6 factorial, 1 times 2 times 3 times 4 times 5 times 6, 720. And I'm writing this just to show you this part. You could also start at the top and work your way down to 1. So obviously it's also 6 times 5 times 4 times 3 times 2, up to, so that's 720. Okay, I myself have these memorized. Okay, I know I've done factorials often enough that I know up to here. Then 7 factorial and so on, maybe not so much, but okay, I would say for sure you should know these. 1 and 1, 1, 1, 2, 6, 24. You kind of want to get comfortable with those. So do I have to memorize them? No. If you know the meaning of factorial, right? You just say, oh, 3 factorial. I know what it means. 1 times 2 times 3, 6. Right? 4 factorial. I know what it means. 1 times 2 times 3 times 4, 24. So you don't really have to memorize it if you know what the factorial symbol means. These two are just by definition. 0 factorial is 1 by definition. 1 factorial is 1 by definition. Okay. So back to 7. A sub n is 1 over n factorial. So I plug in 1, I have 1 over 2 factorial, 1 over 2. Plug in 2, 1 over 3 factorial, 1 over 6. Plug in 3, 1 over 3 plus 1, 4 factorial, 1 over 24, and so on, 1 over 120, 1 over 720. So these are the first 5 terms. And yes, offhand, it looks like this sequence would converge to 0. The numbers are dropping fairly rapidly. Okay. Okay, a little bit more factorial stuff. We can often do ratios with factorials. Now, I don't know what 10 factorial is, pretty big number. I don't know what 9 factorial is, but I can do the ratio fairly easily. Okay. Can you think for a moment what the answer to 10 factorial divided by 9 factorial is? No calculator necessary. You don't have to multiply it all out. It's simply 10 because the top is 1 times 2 times 3 up to 9 times 10, right? 9 factorial is 1 times 2 times 3 up to 9. All of these cancel all of these, so the answer is simply 10. Okay. Here's 5 factorial over 7 factorial. Again, it's not that hard. 5 factorial means 1 times 2 times 3 times 4 times 5. 7 factorial means 1 times 2 times 3 times 4 times 5 times 6 times 7. Aha. The 1, 2, 3, 4, and 5 cancel this 1, 2, 3, 4, and 5 factors. So the bottom has an extra 6 times 7. So the answer is 1 over 42. Okay, let's look at this one. Can you understand this? 99 factorial over 100 factorial. Okay, you should be able to tell pretty quickly it's 1 over 100. Okay. You don't need to know what is 99 factorial. It's a real big number. I don't know what is 100 factorial. It's a real big number. But I know that if I take this divided by that, it's 1 over 100. Same logic as this. This is 1 times 2 times 3, up to 99. This is 1 times 2 times 3, times 99 times 100. So everything's going to cancel out except 100. So the factor is 1 over 100. Okay. 11 factorial over 9 factorial. Okay, it says the answer is 110. Can you tell pretty quickly why the answer is 110? You don't have to work out 11 factorial. It's a big number. You don't have to work out 9 factorial. It's a big number. Right? The thing to realize is, and when you're doing these factorial, you say, okay, which has more factors, the top or the bottom, and how many more? Okay, and then I realized the top has 2 more factors. What does the top have that the bottom does not have? 11 times 10. Then after that, they're all going to match, right? So 11 times 10, and then 9876523 divided by 98765. Those are all going to cancel out. So I just have 11 times 10, 110. All right, now later on, they're going to give us just letters. Well, even though they only have letters, you can still figure it out. This one, n plus 1 factorial, n factorial. I know I'm digressing. I'm not doing actual problems in the homework, but this will save us a lot of time later on. Okay, so first I asked myself, which has more factors, top or bottom? Top. And how many more? Just 1 more. What does the top have that the bottom doesn't have? N plus 1. The bottom is 1 times 2 times up to n. The top is 1 times 2 times n plus 1. All of these will cancel all of these. So I just have n plus 1. Okay. Here's some kind of thing that we will deal with later on in the section. 2n minus 1 factorial over 2n plus 1 factorial. Can you see how they got this? So the same game as I asked myself, okay, which has more, the top or the bottom, and how many more? That usually tells you what to do. So the top means 1 times 2 times 3 times 2n minus 1. The bottom also has 1 times 2 times 3 2n minus 1, but it keeps going for 2 more factors. After that one will be 2n. After that would be 2n plus 1. So all of these would cancel out. I have 1 over 2n, 2n plus 1. Okay. So that's how to handle factorials. Okay, number 9 is a recursive definition. What's called recursion. And you computer science people know something about recursion, perhaps. A sub 1 is 1. A sub n plus 1 equals 5 times a sub n minus 3. Okay, these recursive definitions, they're not like this where you can just jump straight to any term, but you have to get one based on the previous term. I'll show you what I mean by that. The first term is 1, so for a recursive definition, you have to be given the beginning term. A sub 1 is 1. And then a sub n plus 1 equals 5a sub n minus 3. That means to find any term, you take the previous term, multiply by 5, and subtract 3. So example, a2 is 5a1 minus 3. Well, they already told me a1 was 1, so 5 times 1 minus 3 is 2. What's a3? 5a2 minus 3. So it's 5 times the number I just got, 2, subtract 3, 7. Do it again. A4 is 5a3 minus 3. So it's 5 times 7 minus 3, 32. You computer science people know you could set this up with a loop, right? A for loop, just have it repeat recursively, or you can repeat until some condition is held with an if-then statement for you computer science people, right? And finally, a5 is 5 times a4 minus 3. So 5 times 32, subtract 3, punch it in your machine, 157. So here are the first 5 terms of the sequence. 1, 2, 7, 32, 157. So the pattern goes multiply by 5 and subtract 3, 2. Multiply by 5, subtract 3, 7. Multiply by 5, subtract 3, 32. Multiply by 5, subtract 3. You just keep doing that. Okay? So that's a recursive definition. Big disadvantage of a recursive definition compared to these other ones is you cannot jump straight to any particular term. Okay? So like the ones we already did, right? Like, I don't know, 3, problem 3. So what is the 1/1,000,000th term? Just plug in a million. For recursive definition, well, unless there's something special about the recursion, where you can figure it out, there's no way in general to do it. In order to get the 5th term, you have to have the 4th term, but in order to have the 4th term, you have to have the 3rd term. In order to have the 3rd term, you have to have the 2nd, right? Okay, so you cannot jump straight to finding what is the 1/1,000,000th term, because you have to run this algorithm through a million times, which you don't want to do. But you computer science people know, of course, that's very easy to let the computer do all that. I mean, that's what the computer is good at, is, you know, crunching out numbers, where you and I don't feel like doing that, right? Okay, so you would set up a loop for you computer science people to have it keep going and so forth. Okay, so this is recursion. All right, now for most of the rest of the problems for today that I'll show you and continue tomorrow. Determine whether the sequence converges or diverges. If it converges, find the limit. Right, so we're taking the limit as n approaches infinity for all of these. We're never going to negative infinity. There's no such thing as a negative 1st term, negative 2nd term, right? When I say, what's the term of the sequence? It's 1st, 2nd, 3rd, 4th. It's whole numbers in general, okay? No 2.5 term, no pith term, no eth term. You know, there's a 7th term and a 1/1,000,000th term. Okay, but there's no such thing as a 316.521 term, right? So each of these we're finding limit as n approaches infinity. So that's not much different than what we had before in Calc 1, right? So 23 star, do some star problems here. A sub n is 1 minus 0.2 to the n. Yeah, 23 to 55, just find the limit as n approaches infinity. That's basically it. So when n gets big, I mean, just take a 0.2. 0.2 to a super big number is very small, almost 0. 0.2, 0.2 times 0.2 times 0.2 times 0.2, it just gets smaller and smaller and smaller. So this becomes 0. So the limit is 1 minus 0, which is 1. Okay, so the sequence converges. C stands for converges. That means you get a real number. D stands for diverges. You do not get a real number. Okay, I guess I was trying to show you here 39 star. A sub n is cosine n over 2. cosine of a half, cosine of 1, cosine 3/2, cosine 2. Okay. Well, on a unit circle, you're just going to keep going around. You don't approach any number. You just bounce between -1 and 1. Or if you think of the cosine function, it goes like this, right? As n goes to infinity, all the way out to the right, you do not approach any one number. So this sequence diverges. Okay. Here's 25 star, which I believe is 23, if I'm not mistaken. Yeah, it is 23, I think. This really is 23. A sub n is this. All right, you might recall this technique in Calc 1. This is second degree. This is second degree. Divide top and bottom by n squared in red. So you have limit n approaching infinity, 3 over n squared plus 5 divided by 1 over n plus 1. And now for super big N, right? That approaches 0, that approaches 0. So I have 0 plus 5 divided by 0 plus 1. Final answer is just 5. Okay, then I see 29 star. Do I see anything equivalent? Maybe not. Okay, so we'll just go with it. Tangent of this thing. All right, so I want limit n approaches infinity. One of the properties of limits says I can sneak this inside the tangent. Okay, so in other words, just swap these two. Tan comes outside, limit goes inside. Okay. 2n pi over 1 plus 8n. First degree, first degree. So same trick, divide top and bottom by n in red here. That gives you a limit n approaches infinity of canceling 2 pi over 1 over n plus 8. Right, so now when n goes to infinity, this approaches 0. So 2 pi over 8 is pi over 4. So I have the tangent of pi over 4, which is 1. All right, 35. A sub n is -1 to the n over 2 radical n. Aha, that -1, when you see that -1 in this chapter, it almost always means alternating. Plus minus, or minus plus minus plus. Okay, here, when they give me -1 to the n, that means the first term is negative. So negative, positive, and so on. So suppose I want to make the first term positive, then just make this an n plus 1 or an n minus 1. I like n plus 1. Author sometimes says n minus 1. But same thing. So the top's just going to go -1, +1, -1. But look at the bottom. The bottom's getting big, right? Should be a 1 there. 1 radical 1, 2 radical 2, 3. Oh, no, I'm sorry. It is a 2. It's not n radical n. I had it right in the first place. 2 radical 1, 2 radical 2, 2 radical 3, 2 radical 1. Okay, the bottom's getting super big. So the limit is n approaches infinity of a sub n is 0. Okay. Yes, it would be proper to say the sequence converges to 0. Okay, so this one I already talked about. A sub n is cosine n over 2. That diverges. By the way, diverges does not necessarily mean it goes to infinity, although it's allowed to. It just means we don't approach any number. I think the sine one was like that too. Did we have a sine one? Yeah, see 39 there? Yeah, 39 is automatically divergent. Sine of 1, sine of 2, sine of 3, sine of 4, sine of 5, right? You know the sine function just goes up and down, up and down, up and down. So we do not approach any one number. So that one diverges. All right. 37 looks like that, or you can write it like that. So this looks exactly like the one we did over here. 1 over 2n, 2n plus 1. So there it is. So what happens when n gets big? This ratio approaches 0. 1 divided by super big, right? 1 divided by super big is super small. So approaches 0. Okay, 41 is perhaps the last one I was going to talk about, and then I was going to quit. Okay, n squared e to the negative n. It's written that way. Yes, it's written this way, but it means the same thing as this. So we're reviewing something called L'Hopital's rule. Remember L'Hopital's rule or L'Hospital's rule in Calc 1. This is considered infinity over infinity. We're plugging a big number, big divided by big. That's an indeterminate form, but I can use something called L'Hopital's rule, which says if the limit of a ratio gives me 0 over 0 or infinity over infinity. By the way, x is allowed to approach plus or minus infinity also. Then limit as x approaches a of f of x over g of x, or x approaches infinity, is the limit as x approaches a of f prime of x over g prime of x. In other words, take the derivative of the top, derivative of the bottom, to get the same limit. So that means in this case, which was infinity over infinity, take the derivative of the top and bottom. Derivative of the top is 2n. Derivative of e to the n is still e to the n. This is still infinity over infinity. Do it again. Derivative of the top is 2. Derivative of the bottom is still e to the n. So the limit is 0. Answer is 0. Okay, the problem's finished, but a side note. Notice what happened when I kept doing L'Hopital's rule. This went n squared, second degree, then it became first degree, and then 0 degree or constant. But the denominator just stays e to the n. Therefore, this limit, n approaches infinity of n to the 1 million over e to the n is also 0. It's going to take you a while to get down to what you want, but it's going to work. If you differentiate this, it's going to be n to the 999,999 and a million in front, but that stays the same. Take another derivative, 999,998. Take another derivative, 999,997. Okay, after a million iterations, doing it a million times, this will eventually get down to the point where you have a constant. But no matter how many times you differentiate the bottom, it stays e to the n. So the limit is automatically 0. Okay. All right, folks, I was going to call it a day. So I've given you enough to get started, I believe, with section 1, 7.1. So you can try some of these limits. I'll do more of the limits tomorrow. And then we have a few problems at the end, I think, involving increasing or decreasing or not monotonic sequences. And I'll talk about that tomorrow as to what that means. Okay. All right, so I think I'm done. Let me stop the share and check the chat. Anybody with a question, please? All right, then we're done for the day. All right, folks, have a good day, and we'll see you next time. Okay, all right, bye.